So, welcome back here again the second part of today's module. What we are looking for it is the expression of the current as a function of the W's and L's and VGS and VDS, and VGS and VDS of course, they are applied here. And also just to get an idea that how this current is it depends on the device parameter. So, in the next slide we will be seeing that how the current, while the current it is flowing as IDS, how this IDS current it depends on these parameters. Okay. So, what will be the expression of this IDS? So, we do have so this is the big question. First of all, let me quickly put the biases. For vertical field, we do have VGS here. So, that creates vertical field, and let me assume that this VGS it is higher than VTH. So, the first assumption is that this is higher than VTH, that means the channel is existing, and then we apply the other potential. So, we do have the VDS, which is providing the lateral field. First, then if you see here, I think it is let me go with intuitive way that IDS it is proportional to what? It is proportional to W. In fact, it will be proportional to W by L, because if you see here, this is the L and this is the orthogonal dimension is W. So, if you are having higher length for everything is remaining same, it is expected that the resistance here it will increase. So, as a result the corresponding current it will decrease. So, on the other hand, if the W is increasing, the corresponding resistance it will decrease. So, you may say directly that IDS it is proportional to W by L, or you can say that aspect ratio of the channel. Now, how about the other parameters? So, this will be proportional to the conductivity in the channel region, so which is controlled by this VGS minus VTH, which means that whatever the excess voltage you do have beyond the threshold voltage, that is effectively contributing to the conductivity, or it is helping to increase the conductivity in the channel. So, we can say VGS is VGS minus VTH, it is directly increasing this current. And also we do have the lateral field, which is getting produced by VDS. So, we can also say that this is proportional to VDS. So, if I combine all of them, so what we can say here it is IDS, it is say proportionality constant, say K, W by L into VGS minus VTH into VDS. Okay. And this K it encapsulates whatever the device parameter is there. In fact, this K, if you see, if the mobility of the electrons are flowing in this way. So, if the mobility of the electron is higher, of course, the current it will be better. So, mobility of the electrons is there, and also the dielectric constant of the oxide epsilon OX divided by T ox. So, intuitively you may say that this represents the capacitance of this structure, which is per unit area of course. So, for a given supply voltage here, the amount of field it is getting created here, it directly depends on this epsilon divided by T ox, or I should say rather the amount of carrier it will be available, it depends on this ratio. So, from that you can say that this k, which is basically coming from the device parameter, they can be directly written in this form. In addition to that, of course, the device parameter is the VTH, which is which of course, it depends on whatever the doping concentration is there in the substrate and so and so. But as a circuit designer, you may assume that both k is constant, VTH is also constant. So, in summary, what you can say that this expression of this IDS, it is mu epsilon oxide divided by oxide thickness T ox into W by L into VGS minus VTH into VDS. But one important thing we are missing here, it is that whenever we say that VGS is higher than VTH and whatever the excess amount we have, it is contributing for towards the conductivity of the channel. But this is valid probably in this portion. Then if I consider we are applying a voltage VDS, which is a positive, that means the voltage across the structure, it is not same as the VGS here. In fact, that is supposed to be VGD, which is VGS minus VDS. So, naturally the conductivity of the channel towards this drain side and source side, they are different. So, this equation it assumes that the VDS is very small compared to VGS minus VTH, and if the VDS is going to be higher and higher, or it is significant, we need some correction in this equation. So, we are starting with this one with the assumption that VGS is higher than VTH, and also we assume that VDS it is much smaller than VGS minus VTH, and then only this equation is valid. So, if we increase this VDS, let us see what is happening. So, let me go to the probably next slide. So, what we are saying here, it is if VDS it is significant, particularly compared to VGS minus VTH. And so, again let me put the quickly put the bias here VGS, and we do have the VDS. So, we do have whatever L and W's and all these things. And as I said that if the length is sorry, the VDS it is comparable with VGS minus VTH, then the conductivity along this length it is changing. Hence, this IDS its expression as I said need to be rectified, or it need to be changed compared to whatever we have derived before. So, we are keeping the device parameter same as mu n, then epsilon oxide T ox and W by L, those things it is remaining as is, but then the conductivity we need to change. So, let us see what are the changes we need to make here. Towards the source side, we do have the VGS minus VTH, whereas on the other side, or on the other end, namely towards the drain side, we do have the VGD, which is VGS minus VDS minus VTH. So, we need to consider both this part as well as this part, and on an average you may say that let us take average of it. So, we just simply add them, divide by 2. So, what we are getting here, it is we do have, so then IDS, let me write in this space, is this part, let you call this is K, and then W by L, and then if you see here we do have 2 VGSs and then 2 VTH and divided by 2, but then VDS is not there. So, we do have VGS minus VTH minus VDS, and also along with that this is what it is contributing to the conductivity, and then also we do have the VDS appearing as it is providing the lateral field. So, we are applying VDS also. So, we can multiply this by VDS. So, we have VDS by 2 here, this 2 it is coming there. So, we may say that now the new equation it is like this, and this is valid as long as VGS minus VDS it is, which is actually VGD, it is higher than VTH. So, as long as this is getting satisfied, then we can say that the expression of the current is like this. In other words, we can say that the channel is existing here as well as here, but of course, they do have a different strength. So, you may say that the strength of the channel is kind of tapered. So, here it is having strong conductivity, here it is weak. Now, what happens in a critical situation when we are just making this voltage higher and higher, keeping this VGS maybe constant, and such that the conductivity here it is approaching towards 0, which means that if it is VGD, it is exactly is equal to VTH, then what happens? In fact, till that point also this equation is valid. So, let me use this equation and let me put the condition that VGD equals to VTH, or you may say that VDS. So, if I say this is equal, so we can say this is equal to VGS minus VTH. So, then what happens? So, this is what we will see in the next slide, that if we are increasing this VDS and if we are increasing such that this is just at the drain end, the conductivity is approaching towards 0. So, so that is what we are saying here, that what happens if the VGD equals to VTH. Sorry, this comma should not be there. So, VGD if it is equal to VTH, which implies that VDS is equal to VGS minus VTH, and then what we have, the current expression is K into W by L, and then VGS minus VTH minus VDS by 2 multiplied by VDS. Now, this VDS we can replace by VGS minus VTH. So, that gives us the expression here, it is K W by L into. So, this portion it is VGS minus VTH, here also we do have VGS minus VTH, here we do have divided by 2. So, this portion it becomes VGS minus VTH by 2. And we do have VDS, which is also VGS minus VTH. So, directly you can say this is square, and this is what it is happening when at this point the channel is about to disappear. This is referred as something called pinch off. We will not be going in detail of that, but till this point you may say that this equation of this current is valid. If I take this VDS beyond this point, then what happens? Okay. So, again let you consider this equation in the next slide, and then we will see what other things are happening there. So, if the in this condition, if I take the VDS higher than VGS minus VTH. So, if I consider equal, then whatever the equation we do have, K into W by L VGS minus VTH square divided by 2. Now, if we exceed this one, what is happening is, of course, in this portion the channel is disappearing. So, obvious things, it will be the obvious conclusion, or maybe we will be having the tendency that we may say that the current is not flowing, right. And however, we do have the lateral field VDS. So, if the current is not flowing, then of course, from here to here there is no potential drop. So, then what happens? Will the channel will completely break, or what will happen? Practically what happens is that the channel is here, it may be going till some point which may not be really going to the drain end. So, you may say that the point where the channel, it is satisfying a condition that the voltage across this structure, it is exactly equal to VTH. You may say that till this point, or till the left side of this point, the channel is existing, and beyond this one the channel is not existing. The natural question is that then how the current is flowing? Of course, there will be current flow, because this voltage, major part of the voltage, it will appear across a small length, or I should say a small region of this length, and as a result there will be a very strong field. So, you may say that this portion of the device, it is working as same as whatever the device we have discussed here, where at this age the conductivity is approaching to 0, and whatever the current is flowing here, whatever the injection of the carriers are happening, that carriers are basically jumping across this junction from the pinch off point till the edge of the drain. As a result, you may say that the total current, while the electrons are moving in this direction, the total current is essentially defined by, so this IDS, it will be defined by whatever the current is flowing, say through this device, and now the device, it is getting modified, namely its length is getting shortened. So, you may say that this equation, it is again valid even in this condition, only thing is that instead of L, I will be having shorter length. So, let me write that. We do have K, W and also 2 here, and then L minus shrinkage of the length, say delta L. Rest of the things, it is remaining same. So, VGS minus VT square. So, then you may say that okay, I do have delta L, and how do I express from outside? Of course, this delta L, it is getting created by this VDS. So, naturally this delta L, it is a function of VDS. So, we may write this L minus del L as like this. You can you can take the L outside, you can make it 1 minus del L divided by L in the denominator, and then if you take, so that is the denominator part, and then if you take in the numerator, what you can say, it is 1 by L is remaining there. If I assume that this part, it is very small compared to 1. So, by Taylor series expansion, you may take it only one part of it, you may say that 1 plus del L divided by L, and this del L part, it is a strong function of VDS. Since this portion is very small, again it is normally it is considered as 1 plus lambda into VDS divided by L. So, you may say that this part it is getting replaced by this, In other words, we may say that instead of this one, let me directly write L here and let me put this factor 1 plus lambda into VDS. In fact, this is what the equation normally we frequently use, and the condition here is of course, the device it is in this region referred as saturation region. We will be discussing that pretty soon, but please make a note that going from this point to this point, it is having some discontinuity. If you carefully look into the equation, instead of writing this VDS, I should have written this is VDS minus whatever the limiting value, and then only there will be continuity of then only we will be having continuity of the equation from the previous region to this region. However, most of the time we consider that this part it is maybe small compared to VDS. So, we do approximate this whole thing by lambda into VDS, and if you see that this is the limiting value of the VDS up to which it was having different kind of behavior, and if you go beyond this one, the characteristic it is all of a sudden it is having a change. So, we will see that these two regions are having distinct behavior. So, we will be looking into that in detail while we will be comparing this characteristic in the across the two regions of operation in the subsequent slides. So, if we summarize what we said is that the device characteristic it is it can be said it is having different regions of operation. Again quickly we do have the VGS here, and we do have the VDS here. So, that is producing rather that is VGS is generating the channels, the electrons are moving in these directions, and the consequence is that the current is flowing in this direction. Note that the channel is basically getting created by the electron layers, and of course, along with the electron layers we do have the static ions. Those static ions are working as depletion region beyond the channel region, but they do not participate for the current flow. So, current is basically carried by the electrons. Anyway, so the IDS, while this IDS is flowing here from terminal side, we will see this is the IDS. So, as circuit designer we may not be knowing what other things are happening internally, but from the terminal what we can say that some current is flowing and that current is coming back here, and this current is getting produced by the combination of VDS and VGS. So, let us see for this IV characteristic for different conditions of these voltages, and let us summarize that. First of all, if the VGS is less than VTH, so we assume that this channel it is almost very weak, and you may say that instead of saying equal, we may say approximately equal to 0. On the other hand, when the VGS is higher than VTH and then we are applying VDS is positive, but it is less than this critical voltage, you may say that it is less than the VGS minus VTH, which means that even at the drain side we do have the channel. Maybe the channel is stronger here, maybe here it is weaker, but finally we do have the channel is spreading across the length, and with that condition we may say that the current here it is K W by L VGS minus VTH minus VDS by 2 multiplied by VDS. Okay. And of course, this k it is having its own internal device parameter, namely mobility, then dielectric constant of the oxide, thickness of the oxide. On the other hand, if the VGS is say higher than VTH, however, VDS is higher than VGS minus VTH. In fact, this is referred as VD set. Of course, this is not constant, it depends on the VGS, sometimes it is referred as VD set. We will see that why it is called VD set, but whatever it is, if the VDS is beyond this one, indicating that pinch off already happened towards the near the drain end, and the current it is it hardly depends on VDS, and the corresponding expression of the current it is K into W by L into VGS minus VTH square by 2, and in addition to that we do have 1 plus lambda into VDS. Okay. So, ideally as I said that I should have written VDS minus VD set, but all practical purposes most of the time we write VDS. So, this is what the overall IV characteristic equation of the transistor, and if you see here what are the parameters we do have, device parameter. Of course, this is one device parameter, and then we can say this is also device parameter, and also we do have device parameter here. So, these are basically device parameters. Rest of the things are the voltages and the device dimensions, and as I said that for board level design, if the device it is already implemented, which means that W and L of the device it is already implemented, then as a circuit designer will be having flexibility to change this VGS and VDS to get a meaningful current flow. So, that is the IV characteristic. Now, let us look into, if I combine all these equations, if we consider the graphical interpretation of the this IV characteristic in the next slide. So, let us see the graphical interpretation of that. First of all, under this condition, as I said, this current is approximately 0. This is K into W by L, quickly K into W by L, VGS minus VTH minus VDS by 2 into VDS, and then here we do have K into W by L divided by 2 VGS minus VTH square into 1 plus lambda into VDS. So, if you plot this current IDS as function of VGS and VDS, what you can see here, this is of course, it is 0. So, now if you consider this region, so probably you can consider two cases. So, let me keep the VGS constant, and then let you observe IDS as function of VDS, and assuming this VGS is constant, but higher than VTH. So, this equation indicates that VDS is appearing here in a square form, and in fact, it is parabolic relationship. So, if the VDS it is small, and if it is smaller than VGS minus VTH, then you may say that it is going like a parabolic way. So, this is the equation. I should use the other color to represent this characteristic curve. So, this equation it is getting reflected here, but then this equation is valid till this point where V d s equals to V g s minus V t h. And if you go beyond this point, the current it hardly depends on V d s. In fact, typically this lambda is very small. So, we may say that if I ignore this part, the current supposed to be remaining constant. And if I consider some small the actual value of the lambda, it may be having slight slopy kind of things, which means that this change is representing the effect of this lambda, which is referred as channel length modulation effect. The channel length is getting modulated by V d s. In fact, this is similar to base width modulation of the BJT we have considered. So, if you see here the different regions of operation, from this point beyond, the current is getting saturated. So, here we may say that this is saturation region. So, saturation region of operation, and before that it is referred as triode region. Triode region, because the current depends on both V g s and V d s. Sometimes it is also referred as linear, particularly if you see this portion, the device behaves like a linear. So, either we may say it is triode region or linear region. Now, this is for a given value of the V g s. Now, if I change this V g s to some other value, of course, this point it will be changing. So, if I decrease this V g s, but still maintaining this is higher than V t h, we may get lower current, and the corresponding current profile it will be like this, and so and so. So, the boundary between saturation and triode region, however, for smaller value of this V g s, it will come down like this. So, you may say that the boundary between this linear and saturation region, it is having like this equation. In fact, this is a quadratic equation. We will see that why it is really quadratic equation. If you make this V g s smaller and smaller, in fact, if you take it further down, so what it will happen is that current it will be almost getting 0. That means, the corresponding characteristic it will be coinciding with V d s line. So, this characteristic it is referred as I d s versus V d s characteristic. Now, if you see say this equation, in fact, you can try to plot the I d s versus V g s also for a given value of V d s. To start with, let me consider the device it is in for a given value of V d s. So, if I increase the V g s beyond V t h, then only the current it will flow, but before that the current is approximately 0. And if you are increasing this current, if you are increasing this V g s, keeping the V d s constant, and then you may say that the device starts from this region or saturation region, and hence the dependency it is like a quadratic. And if you go beyond some point where probably we are satisfying rather this condition instead of this one, and the device instead of really going like this, it will bifurcate from that, and it may continue to be like a linear one. So, from this point onwards, the device enters into triode region or linear region, and before this point the device it was in saturation region. So, here the device it is in saturation region. So, this is happening for a given value of VDS. So, which means that this point, it is at this point the VDS equal to VGS minus VTH, or rather you may say that VGS equals to VDS plus VTH, right. So, naturally if I increase this VDS, I will be getting another characteristic curve, where this bifurcation it will be probably starting beyond this point, and so on and so on. So, normally this changes we can hardly see. So, in most of the textbook it says that okay, this is quadratic equation. Note that this till this point the current is 0, only the current is flowing beyond this one, and the boundary of between this triode and saturation region, it is nothing but this portion, because this character the boundary point, it is nothing but the VGS minus VTH curve. So, you may say that triode and saturation boundary is nothing but this profile, and this profile it is obtained from this equation, where IDS is basically proportional to VGS minus VTH square. So, that is about the graphical representation. Let us see what are the things we have covered today, or rather so far we have discussed on this topic. We have discussed the basic structure of the MOSFET, and then we also have discussed about the operating principle of the circuit for different biasing situation, and then we have discussed about the IV characteristic of the MOSFET, and then we have discussed about the graphical representation of the IV characteristic equation. Note that whatever the equation we have obtained here, it is not having really a diode kind of equation, but we will be having a tendency to utilize those characteristic equation to represent in the form of equivalent circuit. So, later we will see that how those equation can be used to represent the device by means of electrical circuit modules. So, that will be discussed in detail whenever we will be going to actual circuit containing MOSFET. So, in the next module, similar discussion it will be there as we have discussed today, but then for PMOS transistor. I think that is all today. So, thank you for listening.